In this video, we'll be going over section 9.2, systems of linear equations with three variables. And in this section, we'll just very briefly talk about the graphical representation. What we'll see is that it boils down to system of linear equations with three variables have the same types of solutions. You'll have 0, 1, or infinitely many. Then we'll solve one with substitution, and to really emphasize elimination, we'll do two with elimination and also have a word problem at the end. So the graphical representation, I'm not going to spend much time on this because you probably haven't graphed linear equations with three variables. They are what looks like an infinitely long sheet of paper. But I'll remind you the more important thing is that in standard form, a linear equation with three variables, we have an x, y, and z variable, but all the powers are one, just like with two variables. And this was an example of one. This is the x and y plane. It sort of sits at the bottom. You can kind of think about this being a corner of a room with the wall being what we call the z-axis. But once again, you don't really need to remember much of that. One of the pictures I have here is a picture really depicting the solutions, the types of solutions of 3x3 systems. Because what we're asking is what or how many points do these three pieces of paper intersect? You can get no intersection at all. They're all parallel to each other, which means you would have no solutions. You can have them intersect sort of at a slice of the piece of paper. That's infinitely many solutions. And then you can also have them intersect at a spot right there, which is one solution. These are going to be the two that when you work these algebraically are kind of weird. You're always going to have 1, 0, or infinitely many solutions, but when it comes to solving these, you might actually see infinitely many solutions on the way, and it's not right. So we're going to have to talk about very briefly what happens there, which is I have outlined in the next section. But that is something you have to be more concerned about when you have infinitely many solutions to a system of three equations, 3x3 system. You can definitely get what looks like infinitely many solutions, but it's not really. All right, so I have that outlined right here. Whether you have 0, 1, or infinitely many solutions looks a lot like the same before. If you get an x, y, and z value, there is one solution. If you get two numbers that don't equal each other, there is no solutions. Those are absolutely 100% going to be the fact. The one you have to worry about, it's still most of the time going to be true. In this section all the time when we get the matrices, since it's a little easier to do, not always. But if you get two numbers that are equal, you should get infinitely many solutions. But the important thing is it's possible to get both of these at the same time. What I mean by that is when we solve these systems of equations with elimination or substitution, you have to do it twice. One of them can give you no solutions. One of them can give you infinitely many solutions, right? So it's possible to have both of these. And the question is, which one would you choose? So it's possible to have both at the same time. Which one would you choose? Well, no solutions always overrides infinitely many solutions. Okay. No solutions is telling you two things aren't intersecting, and that's more important. So with three equations, if you get no solutions at any point, you are done. If you get 0 equals 0 or something like that, you must make sure you do not get no solutions as well. So before we begin this, I just want to hit on a refresher. What does it mean for something to be a solution of a system of equations? Well, it means that the solution, if you plug in the numbers to all your equations, they all work. All right, so this first one says determine whether the ordered triple, just because it's 3, it's called the ordered triple, 1, 3, 2 is a solution to the system below. And anytime you have an ordered triple, it's just understood as x, y, and z. So it's asking us if we plug in x, y, and z to all the equations, do they all work? So you must plug into all the equations, not just one, to see if it works. If 2 of them work, but 1 doesn't, then it's not a solution. All 3 of them must work. All right, so let's go ahead and do that. If we plug in x is 1, y is 3, and z is 2. To the first equation, we get -1 minus 3 minus 2, and does that equal -6? That is a yes, so that one's good. Second one, we want to plug in same numbers. We got x, which is 1, plus 4 times y, which is 3, plus 5 times z, which is 2. And the question is, does that equal 23? Well, 1 plus 12 is 13, plus 10 is 23. So that one also works. And then the last one, plugging in the same x, y, and z values, we got 4 times x, which is 1, plus 4 times y, which is 3, plus 3 times z, which is 2. And does that equal 22? Well, we got 4 plus 12, which is 16, plus 6, which is 22, and that one works as well. So they all work, which means it is a solution. So 1, 3, 2 is a solution. Okay, so once again, just a refresher on what a solution means, because graphically, we don't want to try to graph these. We don't really understand what they look like, and I can tell you from experience, even if you do understand, it's very hard to tell what's going on with three-dimensional graphs. All right, so we just know that is a solution because it all worked. Right. So the main idea with solving systems of equations with 3 variables is you're still going to have your 2 ways, substitution, elimination. Those are the main ways without a matrix. Then the goal is to create a 2x2 system inside the problem and solve that, because that's what we did last section. All right, so the goal is to create a 2x2 system to solve that. Right. So here I have the first one. We want to solve the system by substitution, just so I can show you doing one of those. And what I have highlighted here, we want to make sure what you do is you solve for one variable in one equation like substitution method, but you have to plug in the other 2. Okay, you must plug in the other 2, otherwise you didn't really do much. All right, so what I'm going to do is I'm going to take this first equation and solve for z, let's say we solve for z in the first equation. All right, what I want to make sure I do when I make this choice, if I do substitution, is just avoid fractions. So solving for z, solving for y, or x in the first equation, all of them will be fine without fractions. The second equation would also be fine because you could divide by 3 here and everything is still a whole number. What you wouldn't want to do for substitution here is use the third equation, because if I divided by 3 to get y by itself, I'd get a fraction here. If I divided by 4 to get y by z by itself, I would get a fraction here. Okay, so that's really the one thing you want to make sure on, is do not give yourself fractions. Okay, but I'm solving for z and the first equation, and like I said, many options when you do substitution on how you start it. But if we solve for z, I can add the x and y to the other side, just getting the z by itself. And we got z equals x plus y. Right. Now we solve for one variable in one equation. We did that first part. Now we want to plug it in to the other two equations. So I take the second equation in the third equation, and everywhere I see z, I'm going to replace with x plus y. Okay, so we're going to plug in x plus y for z into the other two equations. The second equation, we got 3y plus 3z is x plus y equals -9. And in the third equation here, we got -3y minus 4 times z, which is we're using as x plus y, equals 12. All right, now what's going to happen here, no matter how messy your original equations look, if you do these steps, what you'll notice is we have a system of two equations here with two variables. So this code, then it goes back to last section. What I would do here is just simplify each one of these and just see how to go from there. So we can distribute the 3 through the first one, the -4 through the second one. And the first equation, we got 3y plus 3x plus 3y equals -9. And the second one, we got -3y minus 4x minus 4y equals 12. And I'm going to combine the like terms and simplify one more step. So here on this first equation, we got 3x and 6y on the right part, and that equals -9. And combine our like terms here. In the third equation, we got -4x minus 7y equals 12. All right, now if you want to do this whole thing by substitution, you would get to this step and now substitute one more time. And what I would do here is solve for this one. If we solve for x, we can divide everything by 3 and not have any fractions, so I would solve for x here. Okay, so the idea with substitution, if you want to do it the whole way through, you substitute one equation in your original, plug in the other two, get it down to a 2x2 system, and then you repeat the process. You solve for one of your variables in one equation, plug it into the other. All right, so let's go ahead, and I'm going to take this equation and solve for x. Let me not draw a super long arrow like that. Okay, so we've got 3x plus 6y equals -9. And I'm solving for x for the reason I said before. And it just depends the order you want to do that here. Yeah, the way I did in the last video, which is how I'll do it again here, is just divide everything by the 3 to get rid of the number on the x, and we avoid fractions. So we got x plus 2y equals -3. And to finish getting x, we subtract the 2y to each side. We got x equals -2y minus 3. Now we go ahead and do substitution, meaning we take the equation we just solved for x and we plug it into the other equation. Right, so we take our negative 4x minus 7y equals 12 equation and plug in for x. I'm going to go ahead and now do that. So we got negative 4. In place of x, we got negative 2y minus 3 minus 7y equals 12. Let's distribute that negative 4 through. What you'll see here is we only have y in this equation, so we'll be able to solve for y. We got 8y plus 12 minus 7y equals 12. And if you subtract the 12 from each side and combine our like terms, we've got 0 on the right side, 12 minus 12 went away, and 8y minus 7y is y. We got y equals 0. That will tell us there is one solution because we got a number for y. And now that we have that number, we can plug it in here to get x. All right, we do our what's called back substitution. But once you've gotten one of your letters with these bigger systems, you've really done a lot of the work. You take your equations, plug in to get another one. Sorry for all my arrows on here, but it's just what happens when you do these substitution problems. Okay, so we plug in y equals 0 and we get x equals negative 2 times 0 minus 3. Multiplying by 0 does nothing. We get x equals negative 3. And that almost looks like a y. I'll fix that. Okay, but now we have y equals 0, x equals negative 3. Take that z equation you got at the beginning, z equals x plus y. To get z, we plug in x equals negative 3, what we just figured out, and y equals 0. To our equation z equals x plus y. So we've got z equals negative 3 plus 0, which equals negative 3. And we have our answer finally. We got x is negative 3, y is 0, z is negative 3. If we want to write that, we write x comma y comma z as our ordered triple. And because of the negative 3 here, I'll just remind you, think about the order of the alphabet. X, then Y, then Z. All right, so just the overview, what we did, we picked a variable, solved for one of them in one equation. We avoid fractions. We got an equation, and then we plugged it into the other two. We plugged it into the other two and got a 2x2 system. We simplified it to here. Once we simplified it, we had to substitute again. And I picked once again an equation where I could avoid fractions. So we solved for x in this one. Then over here, we solved for x through this blue part. And we got x is negative 2y minus 3. Plugged it into our other equation. And once we plugged into our other equation, we were able to get a number for y, plugged it into our equation for x to get x, and then we plugged in our x and y to the equation we had for z at the beginning to get z. And that is our solution. But substitution method on top of, you know, being harder to avoid certain things like fractions, it is often messier to go through than elimination, which is another reason why I can't recommend enough. If you like substitution, you can definitely do it, but elimination method is what you mainly want to practice. All right, so the next one here, it says solve the system below by elimination. And excuse me, to outline this, what we do is we eliminate one variable in two equations. So if we get rid of x in two equations, if we get rid of y in two of the equations, if we get rid of z in two of the equations, you'll have a 2x2 system to solve. All right, so that's the main method. And I've got two here to do. This first one I want to point out, it's that preliminary step's kind of done for us because what we have here is a 2x2 system. So if you're following the directions here, the idea would be to eliminate one variable in two equations, as y is already eliminated in these two equations, the way it's given to us. All right, so the thing I want to stress here is that not every single problem you're going to have to do the full-blown parts. If something's already done for you, especially elimination-wise, then just realize that, and you can start from there. Since y is eliminated in these two equations, what we want to do is solve these two. And then if we need to use the first one at the end, we will. So use the first one. At the end if needed. All right, so what I mean by if needed is if we have one solution here, we'll get an x, y, and z value. The only way would be able to figure out y is if we use this equation. It's the only one with y in it. All right, but let's go ahead and separate these two. We got 5x plus 2z equals negative 21, and negative 10x minus 4z equals 41. Now I remember with elimination, what I do is if it's not obvious, something we can just add or subtract the two equations to get something to eliminate, I just eliminate x. Or, you know, for lack of a better term, the one that comes first in the alphabet. And since it's kind of set up in that way, we don't have something obvious to eliminate. I want to eliminate x. All right, and if I want to make x go away, I need to match their coefficients, but missing a negative sign. And what I notice here is I can't really do anything to avoid fractions. Okay, so I don't have anything in common I can divide the first one by. I don't really have anything in common I can divide the second one by to avoid fractions. But I don't need to multiply by the full number, meaning I don't need to multiply this one by 10 and this one by 5. If I multiply the first equation by 2, I'll get 10x here, and that'll do it for me. So I just want to multiply the first equation by 2. The second equation, while I'm not going to multiply anything by it, I am going to rewrite it, keep my work organized. All right, so if we multiply our first equation by 2, we get 10x plus 4z equals negative 42. And the second equation, we got negative 10x minus 4z We didn't do anything to it, but we need to rewrite it, equals 41. Very important to organize your work, meaning every time you do something to an equation, bring the rest of the equations you need along with it, even if you do nothing. Right? We don't really need this first equation till the end, so that's why I'm not rewriting it over and over again. I'm just going to leave it up here, but I am working with these two equations, so I got to make sure I rewrite and keep them in order. But I can eliminate by adding the two equations now. The x's go away and the z's go away, so that is 0. And on the right side, negative 42 plus 41 is negative 1. Now, based on last section, what we would know about this system of equations is there would be no solutions. And remember what I said when we previewed this is that no solutions is king. If you get no solutions, you are done. This has no solutions. There's nothing more to do. Okay, so let me just remind you of that. If you get no solutions, you are done. If you get 0 equals 0 or infinitely many solutions, then you have to just make sure you don't get a no solution as well. Okay, but this one worked out pretty easily for us. We are done. No solutions right here. And we don't need to do anything else. You are done. Just stop here. Can't stress that enough. Don't try to do more than you need to. All right, so the next one has x, y, and z, and every equation. This is legitimately as messy as it can get. Typically, the problems will work out to have nice numbers. We're not going to put crazy fractions in there. So if you use the elimination method, you can really avoid using fractions the entire time. But this one will have to do that preliminary step. We need to eliminate the same variable in two equations and then solve the two equations. Now it's really up to you which one you choose, but I'll go through the process of my thinking because there's not an obvious way to eliminate two of the same variable in different equation. I'm going to just eliminate x in two of the equations. What I mean by obvious is that, if I subtract these first two equations, the y's would go away, but I'm still kind of stuck with this -3 here not matching up. Right. So what I want to do is, the easiest thing to think about is making all the x coefficients match, but one be a negative, or one be positive and two be negative. So what I'm looking at here to eliminate x is if I can make all the coefficients 12 because that's the least common multiple, then I'll be able to eliminate x twice. So I want to eliminate x in two variables, or sorry, in two equations. Okay. And my thinking here, because we do have 3, there's a couple things you might have to think of, but the least common multiple of the x coefficients is 12. So I can make all the coefficients 12 by multiplying. Or -12, because we talked about that negative thing before. Okay. All right, so to do that, if we multiply the first equation by 3, that'll give us a 12 here, so let's do that. If I multiply the first equation by 3, I get 12x plus 3y plus 12z equals 17 times 3 is 51, so I get -51. Now, the second equation, I also want to get a 12 for x or negative 12. It doesn't matter which one. If I multiply the second equation by 12, I will get a negative 12x. So let's go ahead and multiply by 12. All right, so we're multiplying the second equation by 12. We get negative 12x plus 12y plus 24z equals 60. And then the last equation, we already have the 12 there. I'm not going to do anything to it, but I need to rewrite it. Right, I already have the 12 there. It's negative 12, which is fine. But I do not want to forget to write it and neglect it. All right, so these are my three equations. And now I'm going to be able to eliminate x in two of them. All right, here's the very, very important thing. When you have three equations, anytime you do elimination, let's say we want to add the first two equations together. What's really happening is it's replacing one of our two equations. Meaning if I add these first two equations together, the thing I get out can be my quote unquote new second equation. Okay. So what I'm going to do is to eliminate x in one of the equations, I'm going to add the first two equations together. The way I want to think about this is to eliminate x in second equation. Okay, we want to eliminate x in equation 2. The way I'm going to do that is adding first two equations together. And I'm going to do this separated. Right, meaning I'm just going to leave my system of equations here, and I'm going to rewrite the first two and add them together. Right, so let's add these. We got plus, the x will be eliminated. 3y plus 12y is 15y. 12z plus 24z is 36z. Equals negative 51 plus 60 is 9. All right, that's our new second equation. It's one of the two things we're going to use. Basically, we're trying to get to this point here, only we're eliminating x. So it's like our new second equation. All right, now we want to eliminate x in, let's say, the third equation. Well, if I add the first and third equations together, I still get it to eliminate. So to eliminate x in equation 3, what I'm going to do is, excuse me, eliminate x in equation 3, so I'm going to add the first and third equations together. All right, so I'll start by rewriting the first and third from above. We got 12x plus 3y. Clearly going to run out of room. I'm going to write this below. All right, so we got 12x plus 3y plus 12z equals negative 51. And we got negative 12x minus 3y minus 12z equals 51. And we add these together. Right, but what you see if we add these together is everything goes away. 12x and negative 12x cancel out, 3y and negative 3y cancel out, 12z and negative 12z cancel out, so we get 0 equals negative 51 plus 51 is also 0. This is our new third equation. Right, so here's the thing you have to just check. Right, if you see this, you want there to be infinitely many solutions, but you have to be concerned that there could be no solutions, and this could be a false. Well, the only thing you have to worry about as far as the no solutions popping out is that was your new second equation. Right, so when you eliminate the 2 at the beginning, if you get no solutions, you're done. If you get infinitely many solutions without no solutions, we are done. Since this is not no solutions, right, it's just an equation. We have infinitely many solutions as our answer. Okay. And like I said at the beginning, when we started this, that's not really going to pop up in this section, but it will pop up in the next section when we do matrices, so I want to talk about it. But when you do elimination method and you eliminate your 2 variables, or the variable in the 2 equations, if you get no solution in one of them, it's no solution. If you get infinitely many solutions without no solutions, it's infinitely many. So if this had been 0 equals 1 and this was 0 equals 0, we would have no solutions. Okay. But we didn't get no solutions, therefore there's just infinitely many. All right, so the last thing here is just a word problem related to this stuff. And this one, it's similar to the last one. It had a chemist or wanting to make a certain alcohol solution. This one is about acids. But we are told a chemist has 3 different acids. The first solution contains 20% acid, the second solution contains 35% acid, and the third contains 75% acid. All right, so what this is telling you here, this is giving you really your 3 variables. X is, I'm going to call X the amount of the 20%. I'm going to call Y the amount of the 35%. And I'm going to call Z the amount of the 75%. I'm just giving everything a name. Okay, so we've got all our 3 things labeled. Now we want to make equations based on what they tell us. So it says she created 108 liters of a 45% mixture using all 3 solutions. All right, so this really has 2 pieces of information in it, 2 equations. One is that there are 108 liters of the solution in total. So what it's saying is if we add the amounts together, which is X plus Y plus Z, we should get 108. using orange, and not using red. Also that the final solution is 45%. All right, so what that means is remember the last section when we multiplied the amounts by their alcohol percentage, this time if we multiply the amounts by their acid percentage, we'll get another equation. So X is the amount of 20%, we get 0.20X plus Y is the amount of 35%, we get 0.35Y plus the amount of 75%, 0.75Z equals, since it's 45%, it's 0.45 of the amount of 45%, which is 108. So this line gives us two things. It tells us that if we add our three amounts together, we get 108, but also if we multiply them by their acid percentages, what we get. Right, and the last one here, right, we have three unknowns. We need three equations. We have two so far. It says the number of liters of 75% used solution is 3 times the number of liters of 35% used. Right, so if you read that carefully, what that is saying, the number of liters of 75% is Z. And it's 3 times the number of 35% used, which is Y. Right, so Z equals 3Y. Right, this is our three equations here. We made our three equations. And it's asking us to solve for X, Y, and Z. Because we're asked how many liters of each solution was used. All right. So I'm going to go ahead and write these in a more normal way. So they're all in line. We got X plus Y plus Z equals 108. We got 0.20X plus 0.35Y plus 0.75Z. 0.45 times 108, let's just multiply that out. Equals 48.6. And the last one we have is Z equals 3Y. The amount of the 75% used is 3 times the amount of 35% used. What you want to notice about your equations written is substitution is definitely the better thing, because you can substitute Z in as 3Y in the other two equations. We want to plug in 3Y for Z. In our first two equations. Right. So we got this word problem. We made our system of equations, and now we've recognized how we should solve it. All right, so let's begin by doing the substitution. I'm going to plug in 3Y for Z. In the first two equations, we got X plus Y plus 3Y equals 108. That's our first equation plugging in for Z. And the second equation, we got 0.20X plus 0.35Y plus 0.75, and then Z is 3Y equals 48.6. And realize what we did before with substitution and elimination. You take your two equations. When you substitute, you plug them in and then just simplify, but rewrite each one. So let's go ahead and simplify this. Combine our like terms. Here we have x plus 4y equals 108. And here we got 0.20x plus 0.35y plus 0.75 times 3y. Let's just figure that number out. 0.75 times 3 is 2.25 plus 0.35 is 2.6. Plus 2.6y equals 48.6. Right. Now you can solve this using substitution or elimination. There's no rules that say if you start with substitution, you have to do substitution the whole way. The other problems, I just wanted to show you how you would do them the whole way. But we want to solve now this system of equations. It's a 2x2 system. Doesn't matter how you solve it. Since it looks more straightforward to solve by substitution, you might think to do that, but I'm going to use elimination because I always prefer that if it's not easy, quote unquote easy, to do the substitution. And to do elimination, if I multiply the second equation by 5, the 0.2x becomes 1x. And then if I multiply by -5 to get the negative sign, that'll work. I'll multiply second equation by -5. Not going to do anything to the first equation, but like we mentioned prior, you need to rewrite them so you don't lose track of everything. All right, so our first equation, we got x plus 4y equals 108. Multiply the second equation by -5, we get -x. 2.6 times -5 is -13. We get -13y equals 48.6 by -5. Don't know that one in my head. Times -5, -243. All right, and then we add these together. X gets eliminated. 4y plus -13y is -9y. And 108 minus 243 is -135. Continue solving for y. We divide by the -9. Cancel, the negatives cancel out, and y equals 15. All right, y was representing the amount of the 35%, so we've got that one. All right, now you can plug in to get z. You can plug in to get x. I'm just remembering here, one of our equations was z equals 3y, so we can get z pretty easily. So we get z equals 3 times 15, which is 45. All right, so we've got y is 15, z is 45. To get x, there's plenty of things you can do. You could plug it in right here. This was a pretty nice equation. X plus 4y equals 108. So let's do that. Plug into x plus 4y equals 108. There are other equations. You could plug it into this one, but I wouldn't because of the decimals. I wouldn't plug it into this one either. This one might be pretty easy, but whichever one you see to do. Okay, so we plug in 15 for y into our equation. We get x plus 4 times 15 15 equals 108. 4 times 15 is 60. And then we subtract the 60 from each side and we get x equals 48. All right, so we've got our three answers. Just correlate them to the question. X was the amount of 20%, Y was the amount of 35%, Z was the amount of 45% or 75%. And the way the problem's worded, it will tell you to do that. Just plug it in. Okay, but these are the solutions. It's not really written like the other ones because we're doing a concrete word problem here. So the question would probably, the answer box would say the amount of 20% is blank, the amount of 35% is blank if you plug in those numbers.